So what I will do today, I will present a joint effort with Henrik Madsen for the last 7 years or so, where we developed model predictive control for smart energy systems as part of the cities project, as part of the smart cities accelerator projects, and a number of other projects, as you will see. And we have really developed the technology a lot, and such that it's ready for also what we would say business applications. And we will show you some of these and also hopefully inspire you. So essentially, it started with this vision from the Climate Commission in 2010, the vision of energy smart cities on municipalities. That has been our guiding line, where essentially you have a renewable energy systems with a lot of wind turbines in Denmark, also photovoltaic cells on houses or solar panels. You have heat pumps, you have heat storage facilities. And in Denmark, which is an agricultural country, we also have, for instance, biomass in the form of straw, as we will show you some examples of. Also, electrical cars should obviously be integrated in such an energy system. And the question that we had, the research question, could we develop control technologies that could coordinate all these different entities in an efficient and stable manner? So essentially what we wanted to develop in cities, and what I would say we achieved, is that we would like to combine forecasts in the terms of wind power forecast, consumption forecasts, and then also models for the various energy units or entities participating in the energy system. We would then combine these into a planning and control tool that would coordinate all these entities such that they used most efficiently and respected, let's say, temperature constraints and so on, and then essentially dispatch plans to energy units in real time. To do that, we first of all, we had to develop a number of new mathematical and statistical modeling techniques, mostly based on stochastic differential equations. We also developed new optimization algorithms, and we implemented all this on modern computer technology. We were fortunate enough to work with a number of energy companies, such that we could also test this in many cases in real life. One of the most spectacular case studies I was involved in was one where we combined economic MPC and unit commitment together with Ørsted at that time, where we essentially controlled the entire power system on the Faroe Islands for 3 months. What we will also show today is how these technologies can be used for integrated operation of electrical vehicles, batteries, solar panels, and buildings. And that much of this work has also been in collaboration with Carsten Rude from Work Package 3. So essentially, viewing this picture of a control room, that's the vision of Central Denmark. This is what we wanted to achieve. We wanted to make the underlying control technology for control rooms like this that could coordinate a renewable energy system in Denmark and elsewhere. So what is MPC? I will just give you a 2-slide introduction to this, where I explain or try to explain the principles. And then we will show you what we actually did. So essentially, the idea of model predictive control is that we use a model and some historical measurements, as you can see here, to estimate the current state of the system. So that would be the state estimation problem, an extended Kalman filter, or another filtering technique. When we have the optimal state, then we will say, oh, what decision should we make in order to bring the system to some set points, or to use minimum energy or minimum costly energy. And in doing that, we will solve an optimal control problem that will provide a profile like this. And we will then take the first part of that profile and we will implement that on the real system. And all of this we need to be able to compute robustly and in real time. Then when one sample timer has elapsed and we get a new measurement, then we shift the windows as we have indicated here, and we repeat the procedure. Of course, there's a lot of details into how we actually do solve these problems, how we formulate them, and so on. And these details we will not spend too much details on today. What we will emphasize, though, is that many of the models that we do have developed, they are based on data. And even for these cases where we do not have a priori good models, we can actually develop database models. So we advocate to use gray box models normally, but if you really do not know very much about your system, then it can also be entirely data-based models, as we have tried to indicate in this diagram here, where you have a step response, and you can see that essentially we can capture the dynamics with, for instance, a parameterization like this. So just to sum up, our models are adaptive, they are data-based, they combine a priori model knowledge and a posteriori data information, and we are able to predict both the mean values and the uncertainties and develop model predictive control solutions around both of these type of models. So essentially, what we did is we have a wind power forecast, consumption forecasts, any other forecast, and then we have models of the system that we want to control, and then we put that into in this case, what is called a power hub, such that we essentially implement this model predictive control technique for all the energy producers and also energy consumers in a grid. It can be many different types, as we've tried to indicate here. It can be entire decentralized CHP plants, wind power plants. It can be pumping systems, as you will see with sewer systems or other pumping applications. It can be, if you have hydropower, as was the case in the Faroe Islands, it can be that. It can be heat pumps, photovoltaic cells can be taken into account, cold houses, greenhouses, individual homes with local power production, and it could also be aggregation of electrical vehicles and large commercial buildings and other industries. But essentially, we developed technology based on MPC that can coordinate all these type of energy consumers and producers. Key idea is indicated in this one here. So essentially what we do is we combine forecasts, that is typically simplified weather models. We have a hierarchical level of model predictive controllers, where we have economic model predictive controllers that in this case control a number of wind turbines, each with a local MPC on. But essentially, these are the type of model predictive control systems that we have developed and tested out on some case studies. Just to show the case study that we will go in a little bit more detail with, this is where we have abundant wind power in the grid, and then we have a local energy smart home with an electrical vehicle, a stationary battery, a heat pump, and photovoltaic cells on the rooftop. If you look at this vision, this is actually very similar to the vision of a guy from California, Elon Musk. This is his picture of the same thing. So he has the Tesla power banks here. That's the stationary batteries, the electrical vehicle. You cannot see the heat pump, but it is out here. And then you also have solar roof tiles, such that you can actually produce energy on this roof here. So using this vision, we developed a number of new technologies for MPC to actually be able to coordinate such a house and also an ensemble of such houses in an entire neighborhood. So we introduced concepts like multi-level soft constraints, smart ways of taking the storage function in. So that was essentially, we could keep track of the value of energy stored in a system like that. We also developed rather simple models that proved adequate for the simulation, control, and optimization of such systems. And we developed very efficient computational algorithms to solve this with minimal computational resources and very, very fast in real time. So if we look at a house with a heat pump and a smart thermostat, it could look like this. So we have the heat pump we have the heat pump here, we have the radiator here and then we have hot water for showering and so on here. What I should also say before I show you the details, we developed applications of this based on embedded computers, where we used Raspberry Pi type of computers with the intention that this could be locally in the local house, and then they would receive set points from coordinators. But we also developed solutions in the cloud where the local houses only had communication equipment, essentially, to actuate then the signals coming from the cloud, from a central computer. So how does it work? It is described here. So you can see here we then have time varying set points and a lower limit and a lower limit and an upper limit on the temperature. You can see here the green one is the electricity price, time varying, and down here you can see the outdoor temperature and you can see the solar radiation. And what the MPC then does, it essentially controls the heat pump, that is the red one here. So you can see that it essentially turns it on when the power is cheap, in order to keep the temperature in the house within the upper and the lower limit in a cost-efficient manner. So that's the basic idea, the basic functionality of the economic model predictive control that we developed for these energy systems. We then extended it such that we did not only have a heat pump, we also had an electrical vehicle with a battery and a driving pattern. We had the stationary battery, so that this is essentially this vision that was similar to the Elon Musk house. And then you can see also the economic MPC for an individual house like that can essentially turn on or can buy and sell electricity when it's cheap, and making sure that we have the indoor comfort that we desire, and we also have sufficient charging of our electrical vehicle when needed, and again, in a cost-efficient manner. We then extended this to not only one house or one smart house like this, but an entire neighborhood. And the idea was the same. We demonstrated that we were actually able to put the heating and the electrical storage on the batteries in a cost-efficient manner, and still providing all the needs by the end users. So essentially, this was what we did until, let's say, last year, something like that. And then I want to show you a quite recent result that we are very proud of. It's really a result by Christian Tilger that I'm very happy that is a PhD student with Henrik Madsen, and I'm a co-supervisor. But essentially, we took this house here that we wanted to model. And then the really novelty provided by Christian Tilger was that he did not only model the house itself, he also came up with a simplified model of the weather process. So that would be the state variables of the immediate surroundings of this house, combined that with meteorological forecasts, such that he essentially got a combined SDE, stochastic differential equation model, for the house and the local weather process. Put that into an economic model predictive control, where he clearly distinguished between the disturbance forecast provided by this model, so that could be his model on another external provider, and then the MPC. He ran that for 4 different cases, or many cases, but one where he heated the house with only electrical heaters, one where he heated it with the heat pump, one with both heat pump and electrical heaters, and one where he had both heat pump, electrical heaters, and electrical coolers. And the really, really nice result was that he showed that with his advanced forecasts, this is what you can see here, he could provide almost as good behavior as if we have had the utopian perfect forecast. Furthermore, what I think personally is rather important is that with this setup, he demonstrated that the comfort in the case when we combine the electrical and the radiators and maybe even coolers can be much, much improved if you only have heat pumps, for instance, and the electricity cost can be brought down if you only have radiators. So in this way, with this setup, I think this is the way forward to have both comfort and cheap efficient use of power. We also did that for cooling houses. In the interest of time, I will just move on and say it was implemented on the Faroe Islands, as I indicated, as part of one of the PhDs that participated in this. It was actually an industrial PhD, and we ran this for the entire, or did these principles for the entire Faroe Island power systems for 3 months together with Dong Energy at that time, today Ørsted, and a local Faroe Island power company. All this was only possible because we had a number of inventions in algorithms. So one of this is from this paper, where you can essentially see by making novel algorithms for this entire power system, we was more than an order of magnitude faster than off-the-shelf standard algorithms like CPEX, MOSEC, or Gurobi for solving the large optimization problems that needed there. And for the embedded computations, we also invented new algorithms. Again, you can see this here is the size of the problem. The green one is our algorithms. Again, we are several orders of magnitude faster than the best competitive algorithms. So essentially what we are using this for in the next step is that we are then combining this with something that we did in parallel, not directly in cities, some of it actually in cities, where essentially we are then using the power to X concept, where we have a number of CO2 emitting industries like cement plants, steel plants, and some power plants burning waste, for instance. We have a lot of renewable energy and maybe even hydro. And then the central part in this will be electrolysis of water as a way to store energy, electrical energy, but also a way to produce new chemicals like methanol, like methane, and like ammonia. Parallel with the cities, we ran a project with a small startup company in Denmark at that time. Today there are 50 people that could essentially convert natural gas to single cell protein that could be used for feed animals, including salmons in farms like that. And then you can say, oh, why is this related to cities? Well, you will see in a moment. And just to indicate what is possible by collaborating with DTU, we came from the concept, I would say, in these 7-8 years to a factory like this built in Russia. And again, based on the model predictive control technology, this was possible. With this company, we actually, 1 or 2 years ago, filed a patent. They got, based partly on this patent, 100 million Danish crowns in capital from investors. Another PhD project that was related was essentially with gear process engineering, where we developed model predictive control technology that is now sold commercial for milk powder production plants like this that use a lot of energy. And you can ask, oh, why do you bring the milk powder plant and the single cell protein plant in? Well, as part of the cities, we also had meetings with some very visionary people from Ringkøbing Skjern that said, okay, how can we use all the wind power production that is in our municipality, including the new offshore, the power from the new offshore wind parks that will be built? And how can we use that locally with the resources that we have in this municipality that is not, it's the largest municipality in Denmark, but it's also not so many people lives in it, so it's not very densely populated. So it's an agricultural area. Well, they already had a dairy plant where they will produce them, where they have a spray dryer plant. They have a lot of cows. They have a lot of biomass resources like this. They have an enormous amount of wind turbines and solar capacity and visionary minds, like you can see here. And the idea is that one of the ideas that was then proposed is to build a huge thermal storage for this, such that they can run all the renewable energy at full capacity at all time, combine that with boilers, using straw and carbon capture and electrolysis, such that they essentially also produce the feedstocks for a salmon plant like this. So this is a salmon plant in Hvide Sande. So they are, the salmon you pick up in the supermarket are probably grown here, and also for the pigs. And for that, they would then essentially build the single cell protein factory that I just showed you. And all of these then need to be coordinated, and model predictive control technology is what is going to be used here.
John, can I ask you to sum up
Yes.
very shortly?
Yes.
Thank you.
So essentially what we have done is that we have developed a new MPC technology based on stochastic differential equations, new algorithms that we could integrate forecasting and control. And this has been applied in a number of large industrial processes like cement, food, single cell protein, and also in energy processes like the energy system with Ørsted, wind turbine with Vestas, and refrigeration systems with Danfoss. MPC is a mature technology. It's ready to be used, and you're welcome to contact me or Henrik if you would like to hear how you could participate in this or how you could use our MPC technology.